In 3.4, we're looking at graphs of polynomial function. Now let's take a look at the behavior at the x-intercept. An important part in when we're graphing polynomial functions, we really need to look at the x-intercepts, aka roots, aka zeros. In section 3.2 and 3.3, you learned how to zeros, and that is basically where the graph crosses the x-axis. And we used to call this x-intercepts. So at first I want to look at multiplicity of zeros. Let's take a look at this example, x minus 2 squared times x plus 1. This is already in factored form, and if we want to find the zeros or where the graph crosses the x-axis, we set each factor equal to 0. Now what does x minus 2 represent? That means x minus 2 times x minus 2. If we set each of these factors equal to 0, we get 2. We get the same number twice, so instead of writing x equals 2 and x equals 2, we use multiplicities. So here we have actually a multiplicity, let me just draw here, a multiplicity of 2, because x equals 2 is there twice. If this were to be a 3, then we write another x minus 2. I mean, you don't have to write them down. I just want to show you that we get the 0 of x equals 2, which means now our multiplicity is equal to 3. If it's to the third power. So basically your exponent can tell you what the multiplicity is. For this factor we have x plus 1. If we set it equal to 0, we get x equals negative 1. Since we don't see an exponent here, it's understood to be a 1. The multiplicity is 1. And when the multiplicity is 1, we usually don't say that it's understood. Now, if a 0 occurring an odd number of times, so if the multiplicity is 1, 3, 5, this is what this means here. If we have a multiplicity that is an odd number, the graph crosses the x-axis. It crosses through the x-axis. For example, something, so if here's our coordinate system and we graph, and it's crossing through the x-axis, here's x, then that would tell us that the multiplicity is odd. Now, if it is 1, the multiplicity, it basically straight crosses through the x-axis. If the multiplicity is higher, like 3 or 5, it looks more like a cube function, like so. Now, if the multiplicity is an even number, then the graph touches the x-axis. Touching, similar to, well, like a parabola, because a parabola has an even exponent of 2. So it touches. Again, if the multiplicity is an even number, the graph touches the x-axis. It looks like a parabola graph. So it could either, what I call, touch up when the parabola opens up, or touch down if the parabola opens down. So when we start graphing polynomials, we want to look at the multiplicities. We also want to look at the end behavior. The end behavior, when we're graphing the polynomial, it really means what's going on to the far right and what is going on to the far left of my graph. Not what is in between, basically where you see your errors. That's what we're looking at, and there we have a test for this that is called the leading coefficient test. Let me just show you the leading coefficient test rules that you see in the book on page 306. So if you have any polynomial and we have an odd degree, so the leading coefficient test depends on the degree of the polynomial as well as the leading coefficient. Is the leading coefficient positive or negative? So if the degree is odd and the leading coefficient is positive greater than 0, then let me just give you a quick example. As x goes towards positive infinity, so here we have positive x, positive infinity, x meaning y also goes to infinity. So we go to infinity on the x-axis and we go to infinity on the y-axis. Now, if we're going towards negative, if x is on the negative infinity on the left-hand side, you see that your y value is also going down and therefore negative infinity. If n is odd, if the degree is odd and the leading coefficient is smaller than 0, meaning negative, then the graph more or less would be reflected like so. So if x is going towards positive infinity, y would go towards negative infinity, and as x goes to the left towards negative infinity, y goes towards positive infinity. Now, if the degree of a polynomial is even, you really just need to think about the parabola. The parabola opens up if a is positive, if your leading coefficient is positive. So as x goes to positive infinity, y goes to positive infinity, and as x goes to negative infinity, y also goes to positive infinity. So they're both going up. If we have a parabola that's reflected and opens down, now if x goes to positive infinity, then y is negative, and as x goes to negative infinity here to the left, then y is negative as well. So this is basically what this means, and you can see this in your book. And again, here are the graphs more or less. Think about odd degree, even degree, leading coefficient positive, leading coefficient negative. So you can think of the parent function x cubed. If I extend this, here you go. And if n is even, then we have a positive leading coefficient and more or less looks like a parabola. And I'm saying this in not so many words right here. I made a little table here. So if the degree of the polynomial is even and the leading coefficient is positive, then the end behavior is up. If it is negative, the leading coefficient, then the end behavior is down. If the degree is odd, x cubed, for example, then we're going down on the left-hand side and up on the right-hand side. If we have a negative leading coefficient, we go up towards positive infinity on the left-hand side and down towards negative infinity on the right-hand side. And when I say positive and negative infinity, I mean the y values. Okay, so here's an example, negative 5x to the 6 plus 2x cubed minus 2x squared plus 5x minus 10. The degree here is 6 and the leading coefficient is negative. So we have an even degree polynomial with a negative leading coefficient. That would put me into this category, and the end behavior is down. Now, something else is of interest when we graph it, and I call it the turning points, when your graph is changing direction. So here you can clearly see we're going up. then we go down. That's 1 turning point, 2 turning points, 3 turning points, 4 turning points. So this graph has 4 turning points. Then the lowest degree of the polynomial, the degree is always 1 more than your actual turning points, is 5. And the leading coefficient, how do we know, is positive? Well, on the left-hand side, we see the arrow is moving down, and on the right-hand side, the arrow is going up. Down, up means that our leading coefficient is positive. So as x goes to negative infinity, that means f of x also goes to negative infinity. And as x goes to positive infinity, I'm right over here, you see that f of x, or your y value, also go to positive infinity. So here you go. That is the end behavior. Let's take a quick look at this graph here. Now, how many turning points do you see? 1, 2, 3. There are 3 turning points. That means the degree of this polynomial is 4, at least 4, 1 more. And we also see that the end behavior on the left-hand side and on the right-hand side is up. So that tells me we have an even degree. Positive leading coefficient. So here are kind of the steps on how to sketch a polynomial. Again, we're just sketching it. I would start with the leading term, leading coefficient, and the degree. Leading coefficient and degree. And based on this, I know what the end behavior will be. Is it even? Is it odd? Does it go up or does it go down? Look at the list again. Then we're going to find the zeros. Also take note of any multiplicities. Do they cross or touch? Another good point to graph would be the y-intercepts and any other points that get you the shape of the graph. You may want to make a little t-table if you just need to sketch it, and if you just need to find some important points, then that would be sufficient. Sketch your graph, draw a smooth curve using all the information. Also, don't forget the turning point. So let's take a look at this example here. We have f of x equals x plus 1, x minus 2, and x minus 4. The leading coefficient, there's no negative up front, is positive. And if I count all my x's, that means the degree is 3. So the degree is 3. Kind of based on that, I know my turning points. I have to have 2 turning points. If the degree is always 1 more than the turning point, so I need to. Somehow my mic didn't work, so let me just go back down here. Let's hope it's working now. I've been talking without a mic. This is where we left off. The end behavior is down and up. The zeros are negative 1, 2, and 4. The multiplicities are all 1. Since there are no other exponents visible, that means they're automatically 1. And when 1 is an odd number, all zeros are crossing the x-axis. The degree is 3, 2 turning points. For the y-intercept, we said x equal to 0, and when we said x equal to 0, you just multiply 1 times negative 2 times negative. So the y-intercept is 0, 8. So we have an end behavior that starts on the left-hand side with the arrow down, going through negative 1. Then we have to turn somewhere, and we have to go through 8. We're coming down. We have to go through 2, and now we have to turn again because somehow we have to hook up with 4. and we're hooking up with 4 by making another turn. Now how far down or up this turn is going, we don't know unless we were to plug in like an x value of 3 to get the corresponding y value, and we can plot that point, but I don't want to do that right now, so I'm just sketching. Hook up with 4, go up, and there is my end behavior. So here's another example. It doesn't look all that great, but it gets the point across. We have a degree of 4. 1, 2, and 2 here makes 4. The leading coefficient is negative because of the negative. So with that said, we know that the end behavior is down, down. Degree of 4, that requires 3 turning points. The zeros are based on the factors that we set equal to 0, and we get a -3 that has a multiplicity of 1. That means it's an odd number, so it would cross. -2 has a multiplicity of 1, an odd number, it would cross. And then 1 has a multiplicity of 2. We're touching right there. We're finding the y-intercept, which is 0, -6. So I'm going, let me do this again. I'm coming, I know my end behavior is down, down. So on the left-hand side, I make my arrow that's going down. I'm going through -3. I got to turn somehow. How high, how low this is going, I don't know, but I'm turning. I'm crossing through -2. I make a turn. Somehow I have to get through -6. Then I got to go to 1. And touch and go back down. So what is going on here and what is going on here, how far down, how far up I go, I can only determine if I were to plug in many more values for x and would get the corresponding y values. Now I have plugged in this graph in Desmos, and here is the actual, oops, where is it? Here's the actual graph. Okay, let's zoom in. So here's the actual graph. See, we can see how far up is going by Desmos gives us the actual points, which is kind of neat. These are our x-intercepts, aka zeros. Here's our y-intercept, and that shows us how far down the graph is going. Desmos.com, if you plug in the polynomial, it will graph it, which is kind of neat. So this is the actual graph. We have the sketch of it, which means the graph had end behavior that were going down on both sides, and we also were able to find the zeros and the y-intercepts. More or less, that's how we graph. I guess I'm done.